This video covers Part 1 of Section 3.7, Division into Cases. In the previous section, we considered the proof of conditional statements with a disjunction and or in the conclusion. In this section, we want to look at conditional statements with a disjunction in the hypothesis. To prove statements of this form, we use the method of division into cases, which is based upon the equivalence P or Q implies R is logically equivalent to P implies R and Q implies R, contained in Part P of Theorem 1.2.2. According to this equivalence, in order to prove a conditional statement of the form P or Q implies R, we can prove the two separate conditional statements P implies R and Q implies R. We can think of P and Q as representing two cases of the hypothesis. We then prove that the conclusion R follows from each of the two cases. Here's an example to illustrate the method. For the example, we want to prove for all integers a, b, and c with a not equal to 0, if a divides b or a divides c, then a divides bc. The symbolic form for the statement is for all a, b, and c, a divides b or a divides c implies a divides bc, where the domain for a, b, and c is the set of integers z, and we have the additional restriction that a is not equal to 0. According to the above equivalence, this is logically equivalent to, for all a, b, and c, a divides b implies a divides bc, and a divides c implies a divides bc. Starting the proof, we suppose a, b, and c are arbitrary integers with a not equal to 0. We then need to show a divides b implies a divides bc, and a divides c implies a divides bc. To show this, since this is an AND statement, we need to show the two separate conditional statements, a divides b implies a divides bc, and a divides c implies a divides bc. So we think of our first conditional as case 1 and our second conditional as case 2. So we'll start the proof by proving case 1. So to prove case 1, we'll suppose the hypothesis a divides b. We then need to show the conclusion a divides bc. According to the definition of divides, to show this, we need to show there exists an integer k such that bc is equal to ka. Since we're proving an existential statement, we'll go ahead and we'll set up the two columns for our proof. So we need to find a k, and then we need to verify that k satisfies our two conditions. Now, in order to find the k, we could try using the propositional function, but then if we solve the propositional function for k, we'll just obtain k is equal to bc over a. And we cannot conclude from that that k is an integer. So instead of using the propositional function and solving for k, we'll go back to our hypothesis. So our hypothesis is that a divides b. So since a divides b, then we know that there exists an integer j such that b is equal to ja. Multiplying this equation by c, we obtain bc is equal to the quantity ja times c, which we can rearrange and rewrite as the quantity jc times a. So now this looks like our propositional function, with jc taking the place of k, so we choose k to be jc. So we've now found our k, and so we can go over into the right-hand column and verify our two conditions. And for the domain, since j and c are integers, and as usual, z is closed under multiplication, then k equal jc is an integer. And from the work on the left, we have bc is equal to the quantity jc times a, which is ka. So the propositional function holds. This proves the existential statement, so we can then conclude that a divides bc, and this proves case 1. So now we'll start the proof of case 2. So for case 2, we'll suppose the hypothesis, which was a divides c. We then need to show the conclusion, a divides bc. And as before, to show this, we need to show there exists an integer k such that bc is equal to ka. We'll set up our two columns for the existential proof. Now, before continuing with the proof of case 2, here's a few comments concerning this proof and proof using division into cases in general. Note that in both cases, the hypotheses are different, but the conclusion is the same. This is always the case when using division into cases. In this particular proof, the conclusion is A divides BC. To show this, we need to show there exists an integer k such that BC is equal to Ka. Now you'll notice in the proof, I used the letter K in case 1, and then I also started the proof of case 2 using the letter K again. Now, generally you have to be careful not to reuse variables in your proofs. You don't want to use the same letter to represent two different quantities in a proof. So since we used the letter K in the proof of the first case, it may seem that we should use a different letter in the proof of the second case. However, when doing a proof using division into cases, you want to view the proof of each case as independent of one another. So once you've completed the proof of a case, you're free to reuse any of the variables. It's just like you're starting from scratch, essentially. Since the conclusion in each case is the same, it's actually appropriate to use the same letter for both cases. So now back to the proof of case 2. So we're looking for our k, so we can apply our hypothesis. Since a divides c, then there exists an integer L such that c is equal to LA. Multiplying this equation by b, we obtain BC is equal to b times the quantity LA, which we can rearrange and rewrite as BL quantity times A. And now this looks like our propositional function with BL taking the place of K, so we'll choose K to be BL. Now that we've found our K, we'll go over into the right-hand column and verify the two conditions. For the domain, we can say that since B and L are integers and Z is closed under multiplication, then K equal BL is an integer. And from the work on the left, we have BC is equal to the quantity BL times A, which is equal to Ka. So the propositional function holds. So this proves the existential statement, so therefore A divides BC, and this proves case 2. Since we've now proved both cases, then this proves the given statement, and our proof is complete. In this example, the proofs in the two cases are almost identical, with B replaced by C in the proof of the second case. When such a situation occurs in a textbook, the proof in the second case might be omitted with the comment that the proof is similar to that in the first case. However, while the proofs of the separate cases are often similar, in many proofs, the proofs of the cases will be very different from one another and may require completely different approaches. In such a case, we obviously cannot omit any of the individual cases' proofs. Usually, when using division into cases, we do not explicitly write out the cases using the equivalents as I did in the preceding example. So for instance, if we go back to that example, we might write the proof of the statement in the following form. Suppose A, B, and C are arbitrary integers with A not equal to 0. Suppose the hypothesis A divides B or A divides C. We then need to show the conclusion A divides BC. And to show this, we need to show there exists an integer k such that BC is equal to Ka. From the hypothesis, since there is an or in the hypothesis, we recognize that there are going to be two cases. So case 1 will be to suppose that A divides B, and case 2 will be to suppose A divides C. In both of these cases, we need to show the same conclusion, A divides BC, so we would then proceed as before to prove the conclusion in each of these cases. So you'll see that this is essentially the same as the proof that I gave you earlier. I'm just cutting out a little bit of the writing at the very beginning. Division into cases can be extended to more than two cases in the hypothesis using the equivalents P1 or P2 or all the way down to P sub k implies R is logically equivalent to P1 implies R and P2 implies R and all the way down to P sub k implies R. Note that in each of the cases on the right we are proving the same conclusion, which is the conclusion of the original conditional statement. In the preceding example, the hypothesis of the conditional statement is explicitly written with a disjunction. In many situations where we need to apply division into cases, the hypothesis may not appear in this form. Instead, the cases may arise out of a definition involving a disjunction, such as the union of two sets, as in the following examples. Suppose we want to prove for all sets A and B, if A is a subset of B, then A union B is a subset of B. This has symbolic form for all A, for all B. A is a subset of B implies A union B is a subset of B. We'll start our proof by supposing A and B are arbitrary sets. We suppose the hypothesis A is a subset of B. We then need to show the conclusion A union B is a subset of B. According to the definition of subset, to prove this, we need to show for all x, x is an element of A union B implies x is an element of B. So we now prove this universal statement. We suppose x is an arbitrary element, suppose the hypothesis, x is an element of A union B. We need to show the conclusion, x is an element of B. The hypothesis, x is an element of A union B, is equivalent to x is an element of A or x is an element of B, which corresponds to two cases. So we have an or arising out of our hypothesis, and whenever that occurs, that's going to correspond to cases. In case 1, we'll suppose x is an element of A. We need to show x is an element of B. Since A is a subset of B, then x is an element of A implies x is an element of B as required. So this proves case 1. For case 2, we'll suppose x is an element of B. We then need to show x is an element of B. Well, in this case, we're supposing the conclusion, so there's nothing to prove. So case 2 holds. And thus, A union B is a subset of B, which is what we needed to show. The next example was proved in the preceding section using the equivalence P implies Q or R is logically equivalent to P and not Q implies R. Here's an alternative proof using division into cases. So we want to prove for any sets A, B, and C, A intersect B union C is a subset of A intersect B union C. This has symbolic form for all A, B, and C. A intersect B union C is a subset of A intersect B union C. We'll start our proof by supposing A, B, and C are arbitrary sets. We then need to show A intersect B union C is a subset of A intersect B union C. Applying the definition of subset, to show this, we need to show for all x, x is an element of the set on the left, implies x is an element of the set on the right. To prove this statement, we suppose x is an arbitrary element. We suppose the hypothesis, x is an element of A intersect B union C. We then need to show the conclusion, x is an element of A intersect B union C. Now, since x is an element of A intersect B union C from our hypothesis, then we know that x is an element of A and x is an element of B union C. The second part of this hypothesis tells us that since x is an element of B union C, then x is an element of B or x is an element of C. So now we have an or statement arising from our hypothesis. And so this is going to correspond to two cases. In our first case, we're going to suppose x is an element of B, and in the second case, we'll suppose that x is an element of C. Now note that these two cases, again, arise from a hypothesis, not a conclusion. In both cases, we need to show the same conclusion, x is an element of A intersect B union C. Note also that in both cases, we also have the hypothesis from above that x is an element of A. So this x is an element of A, you can think of it as a global hypothesis that applies to both cases. But within each of our cases, we have what you might consider a local hypothesis. In case 1, we have x is an element of B. That hypothesis only applies in the proof of case 1. And in case 2, we have the hypothesis x is an element of C. And again, this only applies in the proof of case 2. So let's look at the proof of case 1. we're supposing X is an element of B, and we need to show X is an element of A intersect B union C. From our hypothesis above, we're supposing X is in A, and for this case, we're also supposing X is in B. It then follows that X is in A intersect B, and therefore X is an element of A intersect B union C, which is what we needed to show. And this proves case 1. For case 2, we're supposing X is in C, and we need to show X is an element of A intersect B union C. Well, since X is in C, it follows immediately that X is in A intersect B union C, and this proves case 2. Since we've now proved both cases, then A intersect B union C is a subset of A intersect B union C, which proves the result.